We recall that for gases, the constant volume, specific heat for monatomic gas is 3/2 R. 5/2 R for diatomic. We've got diatomic written over here, but we haven't. I haven't chosen to focus on it, just to make the picture nice and big. Okay, now, if we expand a gas at constant pressure, the work done is the constant pressure times the change in volume. Now we know that PV equals nRT, so what does P delta V equal? Well, it's nR times the delta of whatever changes in this side, which is T. So that at constant pressure, the only way we get an increase in volume is by increasing T, assuming that N remains constant. P delta V then has to equal nR delta T. It follows that this amount of work, nR delta T, is like an addition to the coefficient of expansion. And this is why we say that Cp equals Cv plus R. And I said coefficient of expansion. I mean specific heat. Okay, so nR is like a specific heat. You multiply it by delta T, and you get an amount of energy. You need this energy to do this work. So you need this thermal energy here to do this work, and that thermal energy has to be added to whatever you do to increase the thermal energy at constant volume to give us the constant pressure, specific heat. In an adiabatic process, there's no thermal energy added. So that if you have an amount of work, P dV, done in a short time interval, or an infinitesimal time interval, you got an amount of work P dV done, then you have to have a change of temperature dT. Because the only way you're going to get this work, since there's no energy coming in from outside the gas, is from the energy of the gas itself. And if you change the gas temperature by dT, you're going to get an NCV dT change in the internal energy of the gas, which goes into this work. Now, P is just nRT over V, so that this P dV is just nRT over V dV, so that we have this equal to this. We can rearrange this easily enough. Bringing the dt and the dV over on this side, we're going to get a dt over t. We get that by dividing through by nRT, just by nt. Sorry. If we divide both sides by nt, this n will divide out, and we'll end up with a t in the denominator. And actually, I guess we're also dividing by the cv, because that ends up in the denominator here. So if we divide by nt times cv and put everything on the same side, we get this equation. Now that's a simple differential equation. We note that we've got this r over cv. Well, that's like r over 3/2 r, isn't it? Or r over 5/2 r, depending on whether we have monatomic or diatomic gas or perhaps something else. If we look over here for just a second, we see that r over cv is your Cp minus Cv over Cv. Let's go ahead and zoom in on that. Because what's the difference between Cv and Cp? It's just r. So r is Cp minus Cv over Cv. Of course, puts that over Cv. Cp over Cv is gamma. Cv over Cv is 1. So that r over Cv is gamma minus 1. So if we come back to the differential equation, we see that the r over Cv dV over V becomes a gamma minus 1 dV over V. So what? Well, so we're going to integrate this term, and we're going to integrate this term. We integrate dt over t, we get natural log of t. We integrate dV over V, we get the natural log of V. Gamma minus 1 times the natural log of V is the natural log of V to the gamma minus 1, just using the laws of exponents. We, of course, get integration constants from both of these terms, and those constants are going to just be expressed over here. This constant will absorb any integration constants that we get from these. Now, the natural log of t plus the natural log of v to the gamma minus 1 is constant. This means that the natural log, now I've kind of skipped a step here, but natural log of t plus the natural log of v to the gamma minus 1 is the natural log of the quantity t times v to the gamma minus 1. And if the natural log of t times v to the gamma minus 1 is constant, then tv to the gamma minus 1 is constant. And the constant has to be positive now, since we had to exponentiate both sides to get this. But you can work through the details of the algebra. It's not particularly difficult. And this, of course, tells us, well, okay, if tv to the gamma minus 1 is constant, let's note the fact that t is pv over nr, so if tv to the gamma minus 1 equals something, then pv over nr times v to the gamma minus 1 equals that same thing. Okay, just substituting pv over nr for t. And then v times v to the gamma minus 1 is just v to the gamma. So we have pv to the gamma over nr. So that tv to the gamma minus 1 is pv to the gamma over nr, which is just a constant times pv to the gamma, since n and r are considered constant here. So that we say that the fact that tv to the gamma minus 1 is constant tells us that pv to the gamma is constant. And that's where the adiabatic gas law comes from.